Hello and welcome to High Voltage Engineering. This is the we are still continuing in the module 2 where we are talking about generation of high voltage and current. We are on the topic of generation of DC voltages. So continuing with from the previous lectures where we have seen different ways of creating converting AC current to a DC voltage, sorry, AC voltage to a DC voltage using rectifiers, voltage multipliers. Now we'll talk about the actual generation of the DC voltages. Okay. Now we'll talk about electrostatic machines, and we'll talk about the basic principle. In electromagnetic machines, current carrying conductors are moved in a magnetic field so that the mechanical energy is converted into electrical energy. This is the basic principle of the electromagnetic machines. We have a conductor which which has a current through it. So when you pass that current carrying conductor through a magnetic field, it will experience a force. Okay, so this is a basic principle of any kind of motors. So in the electrostatic machine, now we are talking, this is electromagnetic machine is for the AC. Now for the electrostatic machines, it is a bit different. In the electrostatic machine, the charged bodies are moved in the electric field against the electrostatic field in order that a mechanical energy is converted into electrical energy. So here what we happen is that instead of the current, we are moving charged bodies in an electric field against the electrostatic field. So that we'll get the mechanical energy is converted to the electrical energy. Thus, if an insulated belt with a charge density of delta is moved in electric field of E, which is a function of x, between two electrodes separated by S, then we have this equation that the charge on the strip belt at a distance of dx is dq, which is equal to delta b dx, where b is the width of the belt. Now again I'll just make a recap. So what we have is we have seen previously the electromagnetic machines. Now we are considering electrostatic machines. In the electromagnetic machine, what happens is that we have a current carrying conductor passing through a magnetic field, and the current carrying conductor experiences a force. Now here in the electrostatic machines, what happens is that we forcefully pass charged bodies in the electric field and against the electric field. And when we pass the charged bodies against the electric field, now how are you passing? By some mechanical action. Now when this is passed, that mechanical energy is converted to electrical energy. Now for example, if we have consider a belt which has evenly distributed charge density of delta. Now consider the width of the belt be small b, and it is against an electric field E, then the force experienced by this charged particles would be the particle density multiplied by the area of belt that is crossing that electric field. Now what is that area? Since its breadth is b and length for an instant b dx, when we consider a small amount of distance, so we have the total force that is given as F equal to Ex into dq from 0 to s, that is equal to integral of 0 to s delta b Ex dx. Now if the belt has a velocity of v, the mechanical power required to move the belt is equal to F into V, that is delta BV into the integral of E dx. So in order to get to pass a charge of delta B dx value through a field of E with a velocity of v, we need to have F amount of force to be applied on it. The current I in the system is given as I become equal to dq dt, and we can, if you replace this dq as delta B dx by dt, that is nothing but delta B into v, the v being the velocity. The potential difference capital V between the electrodes is given as the integral of E dx Ex integral of Ex into dx. This is an electrostatic machine. The mechanical power is required to move the belt at a velocity of v, that is, we have the power equal to F into v, and it is converted into electrical power P, that is given into is equal to V into I, assuming that there are no losses in the system. Now one such electrostatic machine is called the Van de Graaff generator. The Van de Graaff generator is one such electrostatic machine which generates high voltages with a small output current, high DC voltages. So we will be talking about the Van de Graaff generator. So this is the Van de Graaff generator. On the right hand side we have a schematic diagram of the Van de Graaff generator. The generator is usually enclosed in earth metallic cylinder vessel and is operated under pressure or in vacuum. So what you have, this oval shaped vessel, it is actually earth, and it is under vacuum. It's a metallic cylinder. Charge is sprayed onto the insulating moving belt. You can see the moving belt getting inside and out of the of this enclosed vessel. So the charge is sprayed on the insulating moving belt from corona points at potentials of 10 to 100 kV above the earth, and is removed and collected from the belt connected to the inside of the insulating material, insulated metal electrode through which the belt moves. So you spray the charge, and the belt passes inside the vessel, and there are electrode that is where the charges are removed. Okay. The belt is driven by electric motor at a speed of 1000 to 2000 meters per minute. The potential of the high voltage electrode above the earth at any instant is given by V equal to Q by C, where Q is the charge stored and C is the capacitance of the high voltage electrode to earth. The potential of the high voltage electrode rises as a rate of dV dt is equal to 1 by C dq dt, which is nothing but I by C, where I is the net charge in current. Now we will talk about the high voltage electrode in the Van de Graaff generator. A steady potential will be attained by a high voltage electrode when the leakage current and the load current is equal to the charging current. So when we have the potential, when we have the charging current being equal to the leakage current and the load current, we have a steady growth in the potential or the EMF. The shape of the high voltage electrode is so made with re-entrant edges to avoid high surface field gradient, corona and other local discharges. So the shape of the electrode should be made in such a way that there should be low amount of corona or any kind of discharge. The shape of the electrode will be nearly spherical. Okay, so the electrode should be a very almost a spherical shape. The charging belt. Okay. The charging of the belt is done by the lower spray point, which are sharp needles and connected to a DC source of about 10 to 100 kV, so that the corona is maintained between the moving belt and the needles. The charge from the corona point is collected by collecting needles from the belt and is transferred to the high voltage electrode as the belt enters into the high voltage the belt returns to the so basically what we have seen that we have this electrode that is being supplied by the charge contained in the belt. So when the charge is moving up, it is being collected by the electrode and and being and the charge is surfaced on the electrode itself, and then the belt is comes down and again it is getting charged. So but the charging of the belt, it should be such that there should be a very small amount of losses and sparks, or we call it as a corona, or so we have a lower amount of corona, so that and that is basically depending on the construction of the needle. So the charge of the belt is done. The charging of the belt is done by the lower spray point, which are sharp needles and connected to a DC source of about 10 to 100 kV, so that the corona is maintained between the moving belt and the needles. The charge from the corona point is collected by the collecting needles from the belt and is transferred to the high voltage electrode as the belt enters into the high as the belt enters the high voltage electrode. The belt returns to the charge dropped and the fresh charge is sprayed into it as it passes through the lower corona point. Usually, in order to make the charge more effective and to utilize the return part of the belt for charging purposes, a self-inducing arrangement of second corona point system is excited by rectifiers inside the high voltage terminal. To obtain a self-charging system, upper pulley is connected to the collector needle and is therefore maintained at a potential higher than that of the high voltage terminal. So you can see that we have a high voltage terminal being set, which helps into maintaining the charges. Okay, thus a second row of corona point is connected to the inside of the high voltage terminal and directed towards the pulley above its point of entry. Into the terminal gives a corona discharge to the belt. This neutralizes any charge on the belt and leaves the excess opposite polarity to the terminal to travel down with the belt to the bottom charging point. Thus, for a given belt speed, the rate of charging is doubled. So since we have a two charging point here, okay, basically what it says that when you have a two charging point, we have a rate of charge, we have double the rate of charging. Okay, now that we'll talk about the charging current. The charging current for unit surface area of the belt is given by I equal to BV into delta, where B is the breadth of the belt in meters, V is the velocity of the belt in meters per second, and delta is the surface charge density in coulombs per meter square. It is found that if delta is less than 1.4 10 to the power minus 5 coulombs per meter square, to have a safe electric field intensity normal to the surface, with B equal to 3 meters and V equal to 3 meters per second, the charging current will be approximately 125 microamperes. The generator is normally worked in a high pressure gaseous medium, the pressure ranging from 5 to 15 atmosphere. The gas may be nitrogen, air freon, or sulfur hexafluoride. So these are the description of the charging current and the construction of the gas inside of the vessel. Now we'll talk about the uses of Van de Graaff generator. The Van de Graaff generators are useful for a high voltage and low voltage current application. The output voltage is easily controlled by controlling the corona source voltage and the rate of charging. The voltage can be stabilized to almost 0.01%, and they are extremely flexible and precise machines for these are very these are extremely flexible and precise machine for voltage control. So these are the couple of uses for the Van de Graaff generator. Now we'll consider one more type of generator, which is called the electrostatic generator, shown in the figure on the right hand side. Van de Graaff generators are essentially high voltage but low power devices, and their power ratings seldom exceed a few 10 kilowatts. As such, electrostatic machines which effectively convert mechanical energy into electrical energy using variable capacitor principles were developed. There are essentially duals of electromagnetic machines and a constant voltage variable capacitant machines. An electrostatic generator consists of a stator which is interleaved rotor vanes forming a variable capacitor and operates in vacuum. So it is basically a just like a normal AC machine, we have a DC machine. Okay, the electrostatic machine, which we have the stator and the rotor has different vanes which are interlocked between the stator vanes, so they create a variable capacitor. These machines work in vacuum. So this is the calculation of electrostatic generator. The current through the variable capacitor is given by I, that is equal to dV dt plus V dC dt, where C is the capacitor charged into the potential V. Why do you have this expression of V dC dt? Because the capacitor here is not constant but a variable. The power input into the circuit at any instant is equal to given by V into I, that is C V dV dt plus V square dC dt. If dC dt is negative, the mechanical energy is converted into electrical energy. With the capacitor charged with the DC voltage V, the C dV dt becomes equal to 0. The power output will be only equal to V square dC dt. So this is the expression we need to keep in mind, that the power of this electrostatic generator is nothing but V square dC dt, as the voltage here is constant. Now we'll discuss the working of this electrostatic generator. The rotor is now insulated from the ground and is maintained at a potential of capital V. The rotor to the stator capacitance varies from Cm to C0, and the stator is connected to the common point between two rectifiers across the DC output which is minus E volts. Okay. When the capacitor of the rotor is at maximum, that is of Cm, the rectifier B, that is shown in this figure. In this figure, this is a rectifier B. The rectifier B does not conduct, and stator is at the ground potential. The potential E is applied across the rectifier A, and V is applied across the capacitor Cm. As the rotor rotates, the capacitor C decreases and the voltage across the C increases. Thus, the stator becomes more negative with respect to the ground. When the stator reaches the line potential of minus E, the rectifier A conducts, and further movement of the rotor causes the current to flow from the generator. The rectifier B will now have capital E across it, and the charge left in the generator will be Q naught, equal to this expression of C naught into V plus E into Cs plus Cr, where Cs is the stator capacitor to the earth and Cr is the capacitance of the rectifier B to the earth, and C naught is the minimum capacitance value C, that is the stator to the rotor capacitance. Now for the output of the electrostatic generator, the stator will be more negative with respect to the ground. Now a generator of this type with an output voltage more than 1 megavolt and the field gradient of 1 megavolt per centimeter in high vacuum and having 16 rotor poles, 50 rotor plates of 4 feet maximum and 2 feet minimum diameter, and at a speed of 4000 rpm would develop a 7 megawatt of power. Okay, so these are the different electrostatic generator we have discussed. So this is the end of the lecture. Thank you.